Okay, so let me come to a conclusion for the CBE. We have a virtualization here, which uses the NOC and the NOC interfaces to virtualize. It supports different criticalities in principle. It would support that. But there's no protection in one core. So the core itself does not provide any protection between the different parts. And the rationale by IBM was that this is too much overhead. There are nice publications about this CBE, and this is why I always use this as an example. Communication is protected by a strict separation of network communication from the SPE function, and there's a central controller which is used for configuration. The CBE virtualization is originally aimed at security, not at safety. But the functional isolation we found here for security is also can also appropriately applied to isolation in the safety domain. What is missing for mixed time in safety critical systems is really the timing independence, at least a predictable timing for critical tasks, and the traffic classes for different safety and timing requirements are also not possible here. So the main idea of this network level separation, network level isolation is a good start, which we will also use in the following, but it does not fully apply to what we really want. So now I would like to explain you what we did for our own implementations of which is the EDA-MC NOC, and start with the general requirements to a suitable NOC for mixed criticality systems. First of all, mixed critical integration challenges here. We would like to have sufficient function independence, but still allow application communication, as you've seen that in the multi-core example. We would like to reach sufficient timing independence, but still allow efficient scheduling. It doesn't, in our view, make sense to completely separate these parts, for example, with a full TDMA architecture, because people don't accept if you have a many-core system which has low efficiency. Because then the question is, why should I go for a many-core system, and how should I implement this, for example, pedestrian detection, object detection for cars, which has very high requirements? Because we always have a challenge. The more precise these systems are from their functionality, the more performance they require. We cannot say use less performance if the original application then doesn't provide the same safety level. And this is a conflict which we always have when we go to these kind of signal processing and object recognition systems. So we need to look at the infrastructure criticality. And the function independence here means we would like to have independence of inputs and state. Meaning we need memory protection and, as an example, the read and write protection here. We would like to have communication protection for core-to-core communication. And the last thing we found out is important is the interrupt protection. It should not be possible to throw interrupts at other cores. We would like to be able to limit the data flow between different functions, and the solutions are similar to what people are using in the multi-core, maybe memory protection or virtualization. And this whole thing can then be extended to the network level. An example here is the cell broadband engine. So this is what we would like to achieve here with our NOC. Now the NOC we have developed, first of all, the architecture we have is the integrated dependable architecture for many cores, the EDA-MC. It's a configurable mesh NOC here, as you can see. We have up to 4 links per router for the neighbors and also links for tiles. So this is the maximum local element which we can have, 4 tiles on a router. The minimum is 1 tile here. We have 4 to 64 nodes with up to 4 AMBA-based tiles per system. We have NOC level virtualization, and I will explain that in a minute. It includes DMA-controlled data transport, like in the CBE, but also core-to-core communication, directly core-to-core communication, and we included monitoring for timing and power. I will focus on the timing monitoring in this talk. There's also a single system controller up here, which Adam Koscheva has presented in his poster. So we are still working on the protocol there, the control plane, to optimize that system. Functional and timing isolation here is virtualization at the network interface. The core-to-core communication are selectively controlled in read and write direction as required for the communication between safety and non-safety critical systems. All NOC functions are centrally controlled with a network we can call it a network hypervisor if you like. And we have a NOC level timing isolation also, and this is what I will focus on. We have a logic channel virtualization. It's combined with predictable router and global scheduling and a NOC level timing analysis. So let me first talk about the tiles. Each tile is a local system, complete system. So we have two implementations ourselves. We use the Leon 3 core, and Thales is also using our system, and they use a microblaze core. So it's a Leon 3 core. We can use the Leon 3 as a Spark implementation, which is used in avionics, very popular there. All the space applications of the ESA are using Leon 3. It uses an AMBA bus here, an AHB and HBB, APB, and here we added our EDA network interface to the EDA NOC. So basically, each of our tile can be a complete processor system. Of course, you could have a hypervisor there also with local memory management unit and so on. But this is limited because otherwise you need too much space for these elements. Now, the interface here to the system consists of several parts. This is the bus here. You have a master interface and a slave interface. You have a DMA. Most of the transport is DMA controlled. And then here in the system itself, you have the address translation and the routing. Here, packetization, an output buffer, and then also in the opposite direction here. What is added compared, for example, to CBE is a controller here for the output buffer with a monitor, which makes sure not too much communication is going on the SNOC. So in the case of CBE, you get the freedom to access the network whenever you want on the addresses you are allowed to access. Now, we cannot do that because then we can overload the network and somehow run a denial of service attack, if you want, to one of the critical processes. So CBE would not cover that case. But we need to do that. This is why we need this monitoring and control. So that's the starting point. Now, some of the important features here. First, we have an isolation here, a spatial isolation as far as the address space is concerned. So the address space has limitations here. I will show you the table in a second, but also the interrupt requests. So there's a transparent remapping. If we go from one core and communicate to another one, for example, or to global resources, in this case to a memory, you can actually run an address here. You run over the system here, over the route to the shared memory here. In this case, a DDR2, and then access part of that shared access, which is controlled by the address mapping here and the address protection. You can actually change that. And the second core can do the same thing. We need to isolate these accesses here, and I will explain in a minute how this works. So this is transparent for the two cores because it only depends on the programming of the addresses here. We need to do the same thing with the IRQs because, for example, if we get an IRQ from an IO, because there's data has arrived for one of the cores, then we have to map or to route the interrupt to the specific core and then access and generate an interrupt request here on this core 0, for example. But again, this has to be protected and has to be routable. So there's a fine-grained control about which cores can access which memories, and the same thing happens for the interrupt request. So we even have an interrupt request mapping, so certain interrupt here can be mapped to any interrupt here at the level of the core. Now the address translation itself is like here, it's pretty traditional if you like. So there's a page number here, there's a route in which this packet has to be routed, so this route is fixed. And here is the target address, and then we translate this page by page. Here you see there's an offset and a base address here, and this then combines the target address, which then goes into the packetization and together with the routing. So the routing information goes here, and then you have the address information which is added. So this is basically how this is done. So here in this network interface. And one of the issues we always have is how do we get this network interface small? The first one was very big. The first implementation we came up with, we wanted to cover everything, but now we have a smaller one. I will give you data later. Now the IRQ remapping can be seen in the following way. You have a device here which generates an interrupt, a source interrupt, which should eventually go to one of those tiles here. First of all, this is then mapped to the corresponding network interface. So you get a new route. So the interrupt, which arrives here, for example, from an I/O device, also gets a route and a destination interrupt request. And then this is achieved in the network interface of the source. Then it is routed through the network interface controller, and then finally goes to the interrupt request unit of the processor on the other tile. So that's interrupt name and interrupt level. And then finally will start trigger interrupt on the Leon 3 processor on the other side. So that means you need to find, like in the case of addresses, you need to find routes for these interrupts. You also would like to avoid that a critical process is interrupted by a non-critical one, or that a critical process is interrupted at all. You would like to be able to control all these things. And this means interrupts have to be considered here. This is sometimes overlooked. There's no such a possibility in CBE, by the way. Okay, core-to-core communication. We need to protect that. You have seen this in the multi-core example. How do we do that? Same idea here. You set up the mapping here of the address here, and now the address is not the memory address, but it's the address of the different tiles. So the overall memory space does not only cover the shared memories, which are outside, for example, the large memories, but also the memories of the other tiles. So every tile has part, with its local RAM, has part of the global address space. And through the network interface controller, this address mapping, I can also address the RAMs of other tiles. Again, only by configuration of the central controller. It's not willingly from any of those cores. So I can directly write into the global address space, and this way into the local RAM of another tile. Again, this is also not possible in case, this is possible in case of CBE, but not possible in case of AURIX. Okay, then here's the procedure. Set up the mapping here at this point. This can be statically or dynamically done, so you can change these tables at runtime, and then you finally have to assign the IRQ if this message should be accompanied by an interrupt. So if you send some data from here to here, you can combine this with an interrupt from core 0 to core 1. And then finally, you send the data, send the interrupt, and then the tile 1 can read it. So you can combine this way any kind of core-to-core communication. Now let's talk about the criticality issues here. So the network, again, must be designed according to the network traffic with the highest criticality. You've seen this already. The network interface must be separate, must separate the critical from the non-critical tiles, and you have seen this already as a reminder, right? Worst case execution time, activation frequency, communication volume, and addressing. Now, what are the critical parts here? First of all, the translation is certainly critical. If there's an error in here, then you can write into any other tile you like, into any other memory you like. So this must be protected. This is one of the critical parts here. And if you look closer and go into details here, then the upper part here is not really critical. This is part of the local tile. But here the network interface components, you have the address translation and routing. You have the output buffer, which is critical because you must not arbitrarily send anything to the either NOC. Of course, the monitoring, I will explain that later. The packetization must work correctly because otherwise you get failures in the network itself. And this might block the network. I will look at hardware errors. We'll look at this in the context of hardware errors. And in the opposite direction, the same thing for input buffer and depacketization. I will focus on these things mainly. Okay, so the NOC requirements which we derived here are different for the different parts. So the DMA traffic basically transports larger blocks of data between local and global memories. So we have the possibilities to use our local memories in the AMBA-based tiles to get data, to hold local data and to avoid too much network traffic. This is like the Storm is doing that, or also the CBE is doing that. So we have tile-to-tile communication here, tile-to-memory communication, meaning external memory, and tile-to-peripheral communication. That's only the one part. We found out that this is not sufficient because it blocks out a lot of the best effort traffic here. So we also allow local cache line transports. And that also, this puts a lot of pressure also on the protocol and on the memory controller. We have separate time and we have to separate the safety critical from the best effort traffic. And here it's important that we get predictability for the critical traffic. We don't try to completely avoid any interference, but we would like to have predictable interference, meaning maximum impact. And the efficiency here of the NOC is important for all traffic. I think this is clear. In this lecture, I will focus on the DMA and best effort traffic, and I will leave out the cache line transfer. Okay, now the different criticalities, interestingly, use the same links and routers, and that's already the first problem we get. Because we use wormhole routing in NOCs rather than store and forward, we have many more possibilities to get blocking. Because if a packet goes through the system, you get, I will explain that later in detail, you get dependencies between the different flits of a single packet. And that means you have lots of opportunities for blocking. The communication channels, however, must be isolated as far as function and as far as timing is concerned. And we use something which is typical now for NOCs, which are the virtual channels. The virtual channels share a single link. They are scheduled on a link. We use separate queues per virtual channel. That's also typical. And we use scheduling here for minimum interference. And this is one thing we focus on. How can we minimize the impact of the non-critical on the critical one? Or at least control, predictably the interference. So wormhole routing, I already mentioned that, is done. And one thing which is also different to distributed systems is critical links should not have packet losses. And the reason is simple. If you load the memories of these tiles here, the program memories and the data memories, then if you have packet losses on the critical links, then this process cannot work properly anymore. It's not so easy to just repeat packets and to wait for a longer time, such as you do that on the internet. But this has to be on time, and therefore you would like to avoid a packet loss on the critical links. That's at least the idea. Now, end-to-end DMA communication here to show how this whole thing works. We have DMA and RAM and the core here again, the same setup as a minute ago. And then you have different operations. You have a DMA write operation. So one would like to write into 2. And what happens here is that you first set up the RAM on the other side, your own DMA here, and then you basically send the data to the other RAM, so you control it here with the DMA 0. You don't use the DMA 1, so it's the source controlling the DMA transport here, and then you send the data over here. So all the activities happen on this tile 0 when you write into the RAM of the other ones. You don't need any of the resources of the other one, so you don't need to trust the DMA 1. That's the point here. So if DMA 0, if the tile 0 wants to write data to the to one of the address spaces of tile 1, this doesn't need to be trusted. It's only the communication which works here. It's all local. But in the case of read operation, it's different. If you would like to read data from there, it's always the source who uses the DMA. Then you have to send a message over to the DMA1. You request the DMA. Then the core 1 has to program the DMA, its own DMA, then start the transfer later from the DMA here up to its RAM 0. So it's always the sender of a DMA operation controlling the process. Again, you can use the same rationale as we have seen that before. If you read data from another, you need to trust that one. So this one here is at the same level of criticality or even higher than that one here. And therefore, you can justify this operation. And then the direct read operation is also possible. So if you directly read here, you directly send something to the DMA, and then the DMA sends this back. So you remotely program the DMA, and then you do the DMA access. This requires that this DMA is directly accessible by this core, meaning the address space of this core has to be in the address table of the network interface here. So this is something which is a little faster than that one here. That's a direct, but it also requires that you have access to the local resources of this tile. Again, this requires now that this tile here is at the same level of criticality as this one here. Otherwise, it would not be allowed to access this DMA. So there are a lot of little things which you have to look at. But in any case, you need to trust that connection in all three cases and in both directions. Now, the NOC, spatial isolation using the virtual channel and wormhole routing. What is the challenge here? I already mentioned that. So the challenge one is that packets might be blocked and occupy F5 here. You go over multiple routers doing that, and the solution actually is really to use separate queues per connection. So whenever you have a critical connection and you would like to separate that from the non-critical one, you actually use two different queues. And then it solves the problem between the different criticalities, but dependencies within a critical class, they always remain. The challenge number 2 is the transport itself, meaning this has now to do with efficiency. The virtual channel can only hold flits from a single packet. That's how wormhole routing works. And to avoid an inter-packet dependencies, this has been introduced, but you have extra blocking between packets mapped on the same virtual channel. So we exploit that property by setting up streaming connections. Some of our applications, if you look at the car with the image processing, you have streaming data in and out. And DMA also produces streaming data. You basically transport more data than just a single cache line here. And that means you basically reserve such a channel here and then use delimiter flits. There's a head flit and a tail flit. The head flit says, okay, now we start. And then the whole transmission comes, and then we have the tail flit. And this way we reserve a channel for a certain time and increase the efficiency. The efficiency here really is key. Okay, we also have to manage the scheduling here. So we have a crossbar switch in the NOC, and then we schedule the output here, the input to an output router, and there are different ways to do that. There are static isolation approaches, such as using TDMA, and I think the pioneer here was the Etherel network from, at that time, NXP. Then you get a completely independent service by always using TDMA here, which would be something which you will see later in the across architecture. And there's a dynamic isolation using prioritization. There are also examples where people have provided that, examples for that. So there are many opportunities how you can actually run the queues here, the scheduling here in the NOC. Now, one of the issues here is that we don't want to slow down the best effort traffic. The assumption in which we started, and this is somehow also influenced by the implementation you saw from the safety critical steering lock there, is that much of the traffic is non-safety critical. And only part of the traffic is really safety critical, because we would like to minimize the safety critical function because of the cost issues. And that means the traditional approach is to prioritize the critical traffic, which puts best effort traffic as second-class citizen here. And that means they suffer from high latency. Now, problem in NOCs with high latency, if you allow cache line reloads, is that if you have a cache line miss, then you have to wait for that. And that means you increase the load on all the non-critical tiles if you disallow or if you only prioritize the critical traffic. That is tremendous, has a tremendous influence on the efficiency. Therefore, we wanted to avoid this kind of, or to minimize this influence, but still guarantee the properties for the critical ones. On the other hand, the time-critical traffic, interestingly, has little benefit from reduced latency. And this has to do with the design process. The design process for critical tasks is a worst-case design process. You have to guarantee that the system works under worst-case assumptions. That also means that you don't need extra timing. I mean, there is some theory about, or some assumptions about, if you are faster for safety critical processes, then the quality becomes better. But this is not a requirement, typically. The requirement is that the timing, the image processing for the next image of a camera in a car is done in a certain time. Right? And you verify that this is really happening. It's really a worst-case design. Therefore, it doesn't really help you very much to improve the timing there. So it would be best to only guarantee the critical timing here for the time-critical part, and then leave all the rest to the best effort, meaning prioritize the best effort, but only to the limits which we allow for the critical traffic. And the approach we used here is what has been published as back suction. And let me quickly explain how this works. So basically, the utility of the critical ones, which are deadline oriented, are like that. You have basically, here is your hard real-time deadline. Until that time, you have to finish the whole thing. After that, the utility drops to 0 because you have missed the deadline. But before that, if you're faster, it doesn't help you that much. While for the best effort traffic, you have a similar curve here. So the faster you are, the higher is the utility. And the way this has been implemented is by a flow control, end-to-end flow control. It's important that it's end-to-end. So it's controlled by a rate limiter from the sink. So the sink knows exactly how much data it needs in a certain time. And then from that backwardly controls the critical traffic here and increases the priority of the critical traffic if we go under a certain threshold. And this way we can handle the whole thing. We have a very similar, very simple back suction controlling here. Is basically a single signal which says, okay, you have to increase, you have to decrease for each of these virtual channels. So there's a threshold module at every virtual channel, and then there's a rate limit here from the sink. It's a pretty simple algorithm if you think of this, but it's also pretty effective. And that's the important point here, we can analyze it. We can give timing guarantees for this kind of a network. And this is new. So here, this is how this approach works. We use a worst case timing of the critical stream, uses a compositional performance analysis. This is the analysis which we have developed of our chair at our university, and which is also commercialized by the company which I mentioned, SimtaVision. And this is, for example, also used to analyze Ethernet networks and things like this, and CAN networks in a car. So this has been extended to also work with these wormhole routers here at this point and with this virtual channel environment. Has also been published there, the respective references at the end of this slide set. We compared two different strategies. The one is the back suction, which I just mentioned, and the other one is the distributed traffic shaping, where the routers don't communicate but use traffic shapers here to guarantee then end-to-end properties. This is similar as we find it, for example, in Ethernet AVB. Okay, so the whole thing works from the sink backward to the source, and then the respective analysis fits nicely to this compositional performance analysis. Here are the results. So basically, you get a 30% latency improvement for a set of different applications compared to the distributed traffic shaping, which is not much better than the standard prioritized approach. So the standard prioritized approach here, what you can see here is the blue one, and the distributed traffic shaping and back suction are shown down here. So traffic shaping, flow control help you a lot. And of course, the overall improvement on the application performance is only 10% here, because you don't always access these global resources. But the great improvement here is a much better and much easier timing analysis, which helps us a lot in critical traffic. So the summary here is we have an efficient separation of critical NOC traffic with minimized negative effect on non-critical traffic. At least we don't know any better one at the moment. It gives priority to the non-critical traffic and grants requirements of the critical traffic. It exploits at this point the design process, which is fully qualified for the critical ones and non-qualified for the non-critical ones. So we actually exploit the safety standards here. It can be used in many forms of priority assignment. We can also use weighted fair queuing, for example. Doesn't matter. Important is the strategy of only guaranteeing the critical traffic, the timing for the critical traffic with its deadline bounds, not more than that. Unfortunately, back suction does not directly support the publish subscribe traffic, which is very typical in standard systems such as planes, industry, automotive, whatever. So here we have to mimic this traffic and either use copies. This is the form we do at the moment. But this idea of having one sender and then many receivers is something where we need an extra protocol. We will have to work on that in the future. Back suction is only one global flow approach. There are many more possible. The important thing is global flow is better than no global flow in the NOCs. So we should really go for the global flow control if we use the NOC. However, there's a downside, as I will show you later. Now here you see how this is implemented in EDAMC. Actually, we set up the end-to-end connections, for example, from a tile to its memory to get the data through statically at the moment. The dynamic protocols is something which we have not yet done. We would like to investigate that in the future, meaning we have to set up all these lines in the beginning of an application. That also means we have a limitation, because the number of virtual channels is not arbitrary. In our case, it's 8. If we need more than that, we have to open and close some of these channels, which means dynamic control, which is more complicated, needs a predictable control plane, and that's not there at the moment. We investigated, as I said. Now, let's look at the access control here, because the whole thing lives on the fact that we now have separated critical from non-critical one, but we still can overload the network. And that's what you see here. We need the monitoring and the output buffer. Now, we would like to constrain the network from a load of untrusted components, and this avoids buffer overflowing. Buffer overflowing would eventually lead to either back pressure or to lost packets. or lost flits. And this is something which we would like to avoid because it's overhead in the network and because it would make the whole control much more problematic and costly. And we would also like to be able to detect errors for debugging purposes. If there's some process in here which has errors and accesses the NOC too often, then we would like to detect that. So this is the place to go. So the challenge here is the number of the controlled traffic classes. We have many traffic classes, and the cost here grows with the number of the classes we control. And the second challenge, and this is, I think, less obvious, is the complexity of the tile access pattern. Now, we don't have a single software process sitting here. Many of the papers you see just look at a single software process. Now, we have a complex system sitting here in this processor, and if it's a non-critical processor, for example, the access pattern is pretty complicated. There might be interrupts on this tile and different processes in different orders, so the access pattern are changed dynamically. It's not a single access pattern from a single process. And therefore we need, on the other hand, some more complex pattern. We cannot just say, okay, it's periodic, we use a simple bucket shaper or something like this. We have to really take into account that these patterns can be complex, and now not only for the non-critical ones, those are the ones which I just mentioned, but also for the critical ones. You also want to avoid that a critical, this is called fault isolation. If you have a critical core which doesn't work for whatever reason, does have an error, it should not influence other critical cores. That's also something you have to look at. Therefore, you also need the monitor for that purpose. So monitoring is extremely important here. And we had a paper at RTSS 2012 where the idea was to come up with a lean monitor. You don't want to have complicated monitors in these network interfaces because they need space on the chip, which only looks at a consequent number of accesses, which corresponds to the load on the bus, load on the network. And you basically use what you see here is the number of accesses here, and this is the minimum distance between the accesses. So what you do is you try to adapt this. Let me show this. You get these access patterns which are legal. You pre-test these access patterns because of the tests you have, or you have either specified or you have analyzed that in the existing local system. And when you now want to map this to the NOC, you assume that all the individual applications which are integrated are individually tested. If you integrate that to the NOC, you can first derive the legal access pattern as an upper bound. And you see here some of those access patterns here over time, the density of these patterns. And then you can first approximate that with such a linear function. And then from that, one of my students came up with a so-called I-repetitive functions, meaning we define a repetitive function which is repeated after a certain number of steps. In this case, it's, as you can see here, it's 4. After 4 steps, it is repeated, and because of the properties of these functions here, you can guarantee that if you can handle that for a certain window, then you can also manage that for the whole process. So basically, you have a window of 4 to 5. In this case, it's 4 events, which you slide over all the events, and as soon as it follows a certain pattern, in this case, it's very simple. It's a linear pattern. As soon as the distances here are not higher than what you see here, the system is correct, and otherwise it is not. And you would use now this load pattern here for the system itself. Now you can improve this. And this is the work here by reducing this to the bare minimum such that you can eventually, by repeating this monitored section over and over again, you can guarantee that all patterns which have been classified this way are covered by the monitor, but things which go above that would not. So this is a conservative approximation. You would do the approximation like what you see here, as a conservative approximation, and then use the data you get from there in the network design. So it's like a contract. You classify the system, the critical or non-critical system with its property. And the property here is the density of the maximum density of signals and transports. And then you use that guarantee in the network design, and you grant this in the network design. So this is kind of a contracting interface. And this is a big step for us to really control network overload. Let me talk about some implementation and related approaches here. This is an implementation here which we have been doing, which is 4 routers here. Each of them have a single tile, three Leon tiles plus an interrupt controller with a timer outside here in the memory interface. And here are the data. This is used on a Vertex 6 LX760. Oh, I have to speed up. I see that here. That's the implementation on a Synopsys Hubs 62, and you see here the size of that. So it fits nicely on such a system, on a single FPGA, few registers, only lookup tables. So this is not so big, as you can see here from the data. That's an implementation which Thales has been doing. Here you see the respective network on chip. This is the layout here with the cores and the switches and so on. This is the micro-based approach, and here you see 4 routers and a respective number of cores as well. There's a related work in this domain. We have distributed hypervisors over tiles, such as the Spoon-Mona approach. They don't have a NOC. There's the Intel SCC, which is hardware supported, doesn't guarantee any real time. We have been working with that, but it doesn't make any sense for us. It's a good approach for virtualization like the CBE, but it has its serious limitations in timing. The ideas of communicating several local hypervisors with virtual communication channels, links over NOC and beyond chip, Herkersdorf and others in the Aramis project. I will show that in a second, and explicitly supports different criticalities per core. Hypervisor tiles are also possible in EDAMC, but I don't go into that because we gave up on that because it's too much overhead. And there's a time-triggered NOC in the Across project. Here you have the approach by Herkersdorf. You can see that here. You have up here an approach where they really virtualize all the cores. So you have many cores which are virtualized on the same system. Problem is you have non-critical and critical ones distributed over the whole system. So that's one of the issues which we see here. By virtualizing all cores and their interconnections here, makes things much harder. I didn't see a solution from them. Across goes completely different. Across basically uses a time-triggered network everywhere, but only for communication between the cores. And then all the memories are sitting outside. All the local resources are sitting outside, as you can see here. Because if they run this over this network here, they've never shown that. If you run this over the network, you get a lot of extra overhead here, which would slow down the whole thing. Maybe this will come in the future, but the main idea is really the strict isolation with emphasis on fault containment here. I mentioned the issue of fault containment. As a last step, let me quickly talk about something new here, addressing hardware faults. At the moment, we assume that all NOCs work, all NOC parts work. They don't. Because if you have a hardware error, the isolation and the function might be compromised. As you know, the NOCs occupy a significant part of the overall chip area. I've shown that. And that means they also are target to a significant part of the errors. So you have router errors. They must be included in the failure analysis, not only link errors, as you know that from traditional design. And they have potentially complex behavior and not only packet loss or corruption. And the hardware faults can be permanent or transient. And I will focus on the transient figures because they are uglier than the other ones. So what we use here is something which we know from safety standards, which is FMEA. This is the failure mode and effect analysis. And here we will apply it to the network. Now, the procedure itself contains 2 things. You have look at local effects. They are analyzed locally. They look at the local element and find out what are the abstract errors you get there. Right? You identified signals essential for the router behavior. Then you analyze the signal errors what will happen and what are the local effects of an error. And from the local effects of an error, you conclude to the whole network. And that, those are the global effects. And that then leads to network failures, loss of packets, blocked network, and so on. And then you derive the total probability of a global effect from the probabilities of the signal errors leading to the effect. So that's the main idea. You have the switch here. We focused on the switch. You have the signal errors, leads to the local effect. They lead to the global effect, and eventually you can have a network failure. So what we did here is, this is a list of things like flit loss, flit duplication, flit corruption, wrong flit destination. The flit is sent over a different virtual channel through a different port. All these errors can occur. It's a wrong scheduler, wrong signaling, signal is missing. All these things can occur. Then we looked at the size of these different elements, and then we assumed equal error probability over the physical layout, and then came up with a probability of a certain error to happen after we identified which of those features is influenced by which signal. So we get to a relative probability of all these failures to happen. And here, this is a lengthy process. Many students have been involved in that, which come up with a local effect and global effect, and then what is the global permanent effect, the global transient effect, and so on. For example, if a flit is lost, packet is corrupted, and if you don't do anything else, then the virtual channel is blocked. You have to come up with something to release the block. It's a global permanent effect. If a wrong destination, a VC can be blocked, there's a potential failure, and so on and so on. Long lists of these failures. It's really a tedious work. Now, the interesting thing is what can happen. Students came up with 5 classes: quality of service violation, packet loss or misrouting, packet corruption, return route corruption, meaning the signaling back is not working correctly, and the VC buffer blocking. And here you see the number of frequency of, not the frequency, the number of effects, just the number of effects on the table. There's a lot of transient errors for quality of service, but also some static effects, and also isolation is violated. A non-critical message got onto a critical channel. Here you have the same thing, packet loss and misrouting. You see, this is only a small part. Packet corruption. 2, 3 are the traditional ones. They're only a small part. Then you have return route corruption, and very important here with many static effects, the VC buffer blocking. This is something which we have to work on. And here you have if you now assume size-dependent error distribution as I explained, you see here what the relative probability is that, not only the number of effects. You see here lots of transient errors, but also a number of static errors. This is seen here. And of course this is not satisfactory. We found out that we can block the network by a single hardware error, which will then break the criticality issue. We cannot go to higher criticalities under these circumstances. So what we've seen here, switch errors have complex effects. I'll be back I'll be ready in 1 minute. Transient faults can lead to a significant share of static global effects. Even if you have a single transient fault, the thing can be blocked. And this has to do with the fact that flow control and also this issue of wormhole routing is very sensitive to errors. And we have shown this with analysis. We need strategies to recover from errors or pay for the hardware redundancy, which other people try, which is not acceptable in our view. And there are small improvements in protocol. This is something which we have submitted now as a publication. Small improvements in protocol can drastically reduce the static global effects or reduce the errors to a degradation property. So network still works, but it becomes slower. And there's something which is only possible to identify that by using the FMEA. Notice here, FMEA assumes worst case load, so error statistics are conservative, which we give here. Okay. A separation of non-critical NOC traffic with minimized negative effects on non-critical traffic has been pursued with back suction, but there's downside, which we have seen with hardware error. They have a serious challenge to isolation, and we have shown how to analyze that. We have applied here pretty sophisticated approach to resource protection, as I showed, and there are different additional challenges in power and thermal segregation, which I could not cover in the time. Okay, I think this was it. Thank you very much, and I hope I can have some more time for questions.
So, yeah, we do have time for questions. So, don't be shy. Take the time to soak it in. Think about it.
Yes.
Thank you. Is this something that can already be certifiable, or how long do you estimate that this would be something that we'll see in cars?
Okay. So at the moment, I don't think that we can, if you look at the probabilities we have here for static errors, I don't think it's certifiable at this time. We still need more research to really to have a system which is also able to handle higher criticalities. It also obviously it relates to the probability of hardware errors to occur, and this probability is going to rise in the future. This is the problem we have. Now you always have a backdoor, and the backdoor is, as you have seen in the electronic steering, which means you put a second processor next to it, which is simpler, which supervises that processor, and if you have a fail-safe plane, fail-safe function, then you basically have a fallback function to come to a fail-safe function, then you can do that. So the one would observe the other one. And this is one approach we are following in the Certainty project, where we actually use two different implementations. But I think over time we will be able to handle that. It's just we have to work on the protocols. We have to work on details of this architecture to get this done. The fundamental stuff is there, but the hardware error part is still open.
okay, I guess it turned. Oops. Go ahead.
So first of all, thank you for the brilliant presentation. It's a pity that this presentation was just before the poster session, so I had to explain many things from my slide yesterday, and most probably I have done it not as good as you did. So my question is regarding well, when you were talking about resource allocation in Recomp, so there was a slide where you showed the basic software in AutoSAR, and the question is actually why is it so important to go into the multi-core domain if we anyway have our basic software developed to ASIL-D, we can just use these isolation mechanisms on single cores, and in fail operational function cases, we still need another processor running to support our fault tolerance, just because of the power isolation requirements and communication isolation.
Oh yeah, I think you should take it as a first attempt to come up with a multi-core system, because multi-cores are not primarily used to separate these two domains. It makes things easier because you can for example, you can reduce the influence of interrupts, which is always a big issue. But the thing is, in the future, people assume that they can put many functions on the same chip, which are currently dedicated on different cores, and to increase the overall computing performance on the single chip this way. So it's really integrating previously separate implementations on different cores on the same chip. This is going that direction. It's just the higher performance. It's not that you get completely new quality this way. On the other hand, the hypervisor functionality is not used in this strict way in the AutoSAR environment at the moment. So this shielding of the different functions is not so nice, and address space protection and interrupt protection is not so well defined in AutoSAR, such that if you use two cores, this is still a better solution.
Yes, of course. But if you're referring to the avionics domain, where the concepts are coming from, there are already systems like VxWorks or Cisco PikeOS, which offer such level of separation between the between different partitions.
This is right. This is of course a certain overhead which you have there, but the main thing is then the timing. You would like to get a handle on the timing also. And the timing protection is more difficult in these systems. There are exceptions, like the Pharos system, and which have a budget-based approach or a TDMA approach. Those things are working on single cores. But again, it's about going to higher performance on multi-core systems.
Okay, thank you.
Okay, I think we can stop with questions here, and you can always ask more questions in the